All right, we're continuing lesson 2.4 for Math 1. And this one, okay, I made a mistake here. When I was making this, I forgot to put the table around this, so I need to fix it real quick. So if it's not on your notes, please go ahead. I mean, you can add it if you want. You don't have to, but I think it looks better. All right, so we're going to graph these. So once again, pause your video, put your points in, and then unpause, and we'll check. All right, hopefully you have those in. I'm going to go ahead and graph them. So this is -3, +3, so 3 left and 3 up. And then -2, 2, so 2 left and 2 up. -1, 1, negative, so 1 left and 1 up. 0, 0, and then 1, 1 is here, 2, 2 is here, and 3, 3 is here. So this graph has, and it actually continues on in this direction here. I'll just put arrows. And it kind of has a V shape to it. And the reason it does that, this is called an absolute value graph. Now let's talk about absolute value. If we were to measure how tall you are, we took a tape measure, we put it at the top of your head, and we measured, well, no, let's start on the ground. We put it one end down on the ground, and then we brought it up to equal to your height. And we measured your height and said, okay, this is your height. And then we turned the tape measure upside down, and we started measuring from the top of your head down to your feet. We get the same answer. Is that answer negative because we measured it in a different direction? Right, so if we measured your height from the ground up, and then we measured your height from top down, does this suddenly become negative? Is there such thing as a negative height? And this is something that mathematicians realize is sometimes negatives can't be negative. We don't have, sometimes answers can't be negative. And so they had to figure out a way, well, how do we communicate that something is, that it can't be negative, that it has to be positive? Now, one way we could do that is we could say x can't be a negative number. So we could write that out, but I mean, we've talked about mathematicians. They don't want to do this. They don't want it to be really wordy and take a long time. We like symbols. We like to use things that will be more efficient, that'll take less time. And so they came up with a symbol. And that symbol looks like this. Just two vertical lines. And let's say I'm going to put a number here. Let's say we say -6. So we have -6 as our value inside an absolute value. So what we're saying here is, if you put a negative number in here, we don't want you to treat it as a negative. We want you to treat it as a positive. So let's say this -6 represented somebody's height. So they were 6 feet tall, but somebody measured it top down and put -6. This is like, no. We can't have a negative here. Height can't be negative, so it has to be positive. And so that's why we use this symbol to represent that. Now, what if somebody's 5 feet tall and somebody puts it in there? Well, this is already positive. So it's still +5. So we don't have to do anything special with that. All we're saying is, if we put something in here, if somebody puts a negative in, let me rephrase that. If something can't be a negative value, we put absolute values to say, hey, you have to use the positive value. You can't use the negative value. Let me show you one other thing with the absolute values. So let's say you have a problem like this. So you have 2 minus 6 inside an absolute value. Now you might be tempted to go, oh, we can't have negatives and change this. But order of operations applies, and we treat this like a parenthesis. So we would deal with parentheses first, and then you would deal with the absolute value. So you got to simplify everything down to one value before you apply the absolute value. So 2 minus 6 is -4. And then the absolute value says, oh, we can't use negatives, so this -4 will change to a +4. And that's what's happening when you have these values in here. And the equation here is simply y equals the absolute value of x. So if I plug in -3, The absolute value goes, no negatives, so 3. Plug in negative 2, nope, positive 2. Plug in negative 1, nope, positive 1. Now here it doesn't affect anything because these are already positive, so they're good to go. But anytime you plug a negative in, it's just going to flip it and change it to a positive. All right, let's go to the next graph. All right, same drill. Pause the video, plot your points, and then unpause when you're done. Okay, so hopefully you have those graphed in, and we're going to go and start plotting these. So I have negative 2, positive 5. I have negative 1, positive 3. 0, 1. 1, negative 1. And 2, negative 3. And I'm going to connect all these. So this looks linear again, right? And it is. So this is linear. The only difference here, it is decreasing. This is decreasing. Where the other linear equation that we saw on the front page was increasing. But all the points line up, so it is still a linear equation. And the rule here is negative 2x plus 1. And so same type of drill here. If you take one of these numbers, let's say we take 2. I'm not going to do all of them, but if x equals 2, then you would have negative 2 times 2 plus 1. Negative 2 times a positive 2 is a negative 4. And negative 4 plus 1, that is a war. Negatives win. So you get a negative 3, which is exactly what the table tells you. So this equation here would build all these values in this table and any values along this line. All right, and now we're going to talk about the stopping distance that we talked about in our warm-up. So this is actual data for stopping distance. I don't know what kind of car or what this, where this data came from, but this is kind of a sample data of what it looks like. And let's take a look at the doubling. If I'm going 30, it takes 89 feet to stop. If I go 60, which is double, well, double of 89, 89 times 2 is 178. Well, that's not even close to 268. So we can see doubling that distance doubling that speed more than doubles that distance. It's quite a bit more. And so we don't have that kind of straight relationship there where it's a doubling. Let's go ahead and graph these points. So we're going to go to the back page here. I'm going to go ahead and write the values here real quick. I just copied down these values on the back of the page. If you get a later version of these notes, hopefully I put them over here on the side so you don't have to do that. But yeah, so I would have just copied them over from the other side. And now I'm going to go ahead and write out my values. These are my x values. These are my y values. So here along this axis, I need to have values 30 to 80. So I need to put them here. And it looks like going by tens makes sense. So I'm going to go 10, 20, 30, 40, 50, 60, 70, and 80. And then here it gets up to 439. So I'm going to have to guess. These numbers aren't going to be easy to graph because I have to have fairly big jumps to fit all this data in. But I can't be as precise. So we're just going to have to make our best guess when we do this. Boy, let's see. I think if we go by 20s, let's say 20, 40, 60, 80, 100, 20, 40, 60, 82, 20, 40, 60, 80, 300, 20, 40, 60, 80, 400. Well, then I can't fit 439. So I think I'm going to have to go by 25s. So this is 25. So I'm going to label this as 50. I'm going to skip one. That's 25. That's 50. That's 75. That's 100. I don't have to label every single one. You can if you want. 125, 150, 175, 200, 225, 250, 275, 300, 325, 350, 375, 400, 425, 450, 475, 500. All right, so now I have, going by 25s, each movement represents 25 feet, right? So this is distance in feet. Actually, it's stopping distance. In feet. And then this is going to be the speed of the car, and that is in miles per hour. All right, so we should have all our values here. I think we're ready to graph. All right, the first one is 30, 89, so 30. See, that's 50, that's 75, that's 100. 89's got to be somewhere between 75 and 100. I'm just going to take a guess and put it right about there. Now let's take a look at 40, 139. So 40, there's 100, there's 125, 150, so 139 somewhere around here, I think. And this is kind of, you're just making your best guess. 50 and 198, that's almost 200. So I'm going to go 50, almost up to 200, and just put the dot right underneath the 200. 268, so it's 60, I'm going to go 250, that's 275, so 268 should be a little bit below that. 70 is 348, so 70 I'm going to go up to, there's 3, 48 is going to be just under 50. And so 80, 439, so I'll go up here, 450, that's 425, so 439 is going to be somewhere there. And if you look at this graph, you can see that it is curving upward. It is not a straight line. If I try to put a ruler to it, I mean, it doesn't fit a ruler. This is not linear, right? Because it keeps going up. This actually is closer to that quadratic or parabola. It's kind of a U-shaped curve. It's just kind of the right side of the U. And so when mathematicians see that type of thing, they can actually start to understand what type of an equation could model this situation. When they start gathering data points and putting it on a graph, they can have an idea of what type of relationship with it. So seeing that it's not a line, then we know that doubling thing is not going to work. And then this last one's an extension. This was just if students finished some stuff early in class and they were looking for something to do, they could go through and work this problem. I'm going to do it super quick. This one here, -3, and now they want a -1/3. Well, that would be -1. That would be a half. So -1/3 would be somewhere here. -2, -1/2 is there. -1, -1 is there. There's no value for 0. And then if we come over here, 1, 1 is one of the points. 2, 1/2, and 3, 1/3. So you're only seeing part of this graph. And so it's the question that I have for you is, what's happening to the numbers? What are they doing with x to make it into these y values? So 1, 1 is unchanged, but 2 is now 1/2, and 3 is 1/3. So if you said, well, it looks like they're like flipping this, like the 2's going to the bottom, the 3's going to the bottom, you would be correct. This equation is 1 over x, and this is called a reciprocal or inverse. So we'll say it's a reciprocal, and a reciprocal is just a flipped fraction, right? So if you had like 2/3 and 3/2, those would be reciprocals if they're just flipped. If you remember when we did the division, we did copy dot flop for the division of fractions. Well, that flop part, when you flip the fraction, you're creating the reciprocal of it. And this graph actually is really interesting because it does wind up going this way. It gets closer and closer to 0 because then you have 1/4, 1/5, 1/6. So these numbers get smaller and smaller and they approach 0. Over here, they do the same thing. They approach 0, but from the bottom, so from negative values, but still getting closer and closer to 0. And then here the graph actually gets bigger. Well, it goes more in the negative direction. I want to be careful in how I say that. And on this side, as we approach 0, it does get bigger. So this is called, like I said, a reciprocal or inverse function. And so the main thing I was looking for is to see if people would notice the pattern that these numbers are being flipped. All right, that finishes 2.4.